Hello, welcome to Noise Measurement and its Control course again. Today is the second day of the second week of this course, and what we will do today is continue our discussion on decibels, and we will learn how to add up decibels if there are more than one signals present. So, the theme of today's discussion is going to be adding up decibels. Okay. So, what do we mean by adding up decibels? So, essentially what I imply is that suppose there is one source S1, there is another source S2, and we have a microphone here, and let us say source 2 initially is not active. So, only source 1 is working, and let us say my decibel level is LW1 only in presence of the first source, and only in the presence of second source my decibel level, when the only second source is present and first source is not present, it is LW2. Then the question would be that when both of these sources are present, what is the total sound level? So, in this case it is W, so I will say sound total sound power level. What is it? Now, there may be several ways to do this, and some of the ways may be correct, some ways may be approaches may be wrong. One would think that maybe if because of S1 it is dB1 and because of S2 if it is dB2, then I just add them up and that gives me dB3. So, in this case what we are doing is adding up decibels. This is one way to add it. So, first we will write what are several possibilities and see whether it makes sense or not. So, suppose in first case it is 100 decibels and dB2 is 20 decibels, I just add them up and I say oh, it is going to be 120 decibels. Is that correct or is that wrong? We will see it. The other one could be that I actually instead of adding up dBs, I add up watts. So, first I calculate the watts emitted by source 1 and I calculate watts emitted by source 2. I compute total amount of watts which will be received by our microphone or by the ear, and then from that I calculate dB3. So, in this case I am adding up power or energy per unit time. So, this is another one. The third could be I back calculate pressure P1, because its source 1 is going to generate some pressure at the microphone level, and I calculate pressure from source 2, add them up, I add them and I get third pressure P3, and from that I get dB3. So, here in this approach I am adding up pressures. Now, which one is right? Well, one thing I can say for certain is that this approach is certainly wrong. This is wrong. Okay. So, we never add up decibels. Okay. This approach, it works for uncorrelated sources, and we will explain that. So, if there are two sources which are uncorrelated, and we will explain what is meant by correlation. If two sources are uncorrelated, then we compute the wattage associated with each source and add up the total watts, and then we get the final decibels. for uncorrelated sources. And the third one, where we add up pressures, this is also okay, but this is only for correlated sources. This is for correlated sources. So, if we have uncorrelated sources, we use the power method. If we have correlated sources, then we use the pressure method to compute the overall decibels when several sources of noise or sound are active. So, now we will discuss some more details about these methods. But before we do that, we should know what is a correlated, so what are correlated and uncorrelated sources. Okay. So, what do we mean uncorrelated sources or correlated sources? So, consider two loudspeakers, and both these two loudspeakers are getting the same signal. Okay. They are getting the same signal. So, when the sound from coming from first speaker goes up, sound from the second speaker also goes up, because it is getting the same signal. So, when sound is going up in the first case, sound is going up in the second case. When sound is going up down in the first case, same thing is happening in the other case also. So, in this case, the change, the behavior of the signals which are being generated from both these speakers are, they may not be exactly same, but they are similar. Okay. So, they may not be exactly same, because maybe less current is going in the second speaker. So, it is producing less sound, but when first one goes up, second goes up, when first goes down, second goes down, and so on and so forth. So, in that case, so in correlated sources, if the signal from first source is y1 is A sin omega t, then the signal from the second source is also similar, but its amplitude may be different, B, but the frequency will be same, otherwise it will not go up and down at the same time if the frequency is not same, right. So, sin omega t, but there could be a phase difference, there could be a phase difference. Okay. So, if I have to plot this on a graph, maybe the first source looks like this, and this is A, and the second source, it has a phase difference so it goes like this, okay. And this amplitude may be slightly different, or it could be totally different, and let us call it B. So, the amplitude could be different, but frequency will be the same, and there could be some phase difference, phase shift. So, in this case, these two signals are correlated, because I know the mathematical relationship between the behavior of first signal and the behavior of second signal. I know the relationship, how I can predict that if y2 is going to be something, then what will be y1, because I know the exact behavior. Okay. Now, in uncorrelated sources, this is not true. uncorrelated sources, this is not true. For example, there are two individuals talking, right. So, one person is source 1, another person is source 2, but you cannot correlate, you cannot have a mathematical relationship between what the person A is talking and what the person B is going to talk, right. So, the behavior of person 1's sound has no mathematical relationship or bearing or influence on what the second person is going to say, right. So, here there is no correlation between sources sound coming from two different sources. Okay. So, those are uncorrelated sources. So, example as I said, or two persons talking. Another example could be two different machines, they are generating sound, but they do not know each other. So, machine 1, noise from machine 1 is independent of the noise coming from machine 2. There is no mathematical relationship between two different type noise. So, this is there. So, if the signal is like this, then, so again I will, so this is source 1, this is source 2, this is the microphone where we are measuring, and if the nature of signal at the location of measurement, which is here, not at S1 or not at S2, at the location of measurement is Y1 and at the location of measurement is Y2 because of S2. Okay. Then if both the sources are active, then what will be the total signal? It will be Y1 plus Y2. Okay. It will be Y1 plus Y2. And I know the relationship between Y1 and Y2, so I can add them up. Now, if Y1 is pressure, then if the pressure due to signal 1 is P1 and pressure due to signal 2 at the location of measurement is P2, then at the location of measurement total pressure will be P1 plus P2. In that case, we use this approach. We add up the pressures. And we compute the overall decibel level. However, if the sources are uncorrelated, so what does that mean? Suppose there is a person and there is another person and both of them are talking something, and we have a measurement here, measurement device, and the signal is coming at this location. I do not know what is the mathematical correlation between the signals coming from these two individuals. So, I cannot add up these two things, right. So, I cannot add up these two things, but what I can do is that I can compute the energy which is coming at this point from source 1 per unit time, which will be W1, and I can also measure energy coming to the location of the microphone from source 2 per unit time, which is W2, and I know that I can add up energies because the energy does not get destroyed. So, at that location the total energy will be W1 plus W2 per unit time, it will be per unit time. So, if there are uncorrelated sources, then this is the method we use to compute the overall decibel level. There are uncorrelated, and we will explain this further by example. This is how we add up. Okay. Now, it should be understood that when I am talking about energy, so this is time, let us say this is watts, and let us say the watts is like this, When I am adding up energy, I have to add up energy over a period of time, right, not at 0 time, because in 0 seconds how much energy will be coming? 0. Only in a finite amount of time I can add up energy. So, this is a plot of power with respect to time. So, I have to add up the energy over a period of time, which means when I am adding up energy, I am doing this addition over a period of time, which indirectly implies that this method of adding the energies works in a statistical sense, because it is not at every instant I am doing this. I am adding up over a finite period of time, and then based on that I am calculating the overall sound power level. Okay. So, this is important to understand. So, let us do a couple of examples. So, let us say, so we will do for two uncorrelated sources. Two uncorrelated sources. So, let us say I have a source S1 and it is generating LW1, and that is equal to 51 decibels. And then I have a source S2, it generates LW2 and that is equal to 55 dB. So, these are sound power levels, these are sound power levels. So, then the question is total LW in presence of S1 and S2 is how much? When both the sources are active, what is the overall sound power level? So, because these are uncorrelated sources, I have to add up the wattages. Okay. So, what that means is, first I have to calculate the total amount of watts. So, LW1 equals 10 log 10 W by W ref, which means W equals, and LW1 is 51. So, 51 divided by 10 into W ref. This is my wattage of the first source, and LW2 is equal to 10 log 10 W2. So, this one W1. So, W2 10 to the power of 55 divided by 10 into W ref. And what is W ref? 10 to the power of minus 12 watts. This is something we had defined yesterday or last week. So, W1 equals 1.259 into 10 to the power of minus 7 watts, and W2 equals 3.162 into 10 to the power of minus 7 watts. So, W3, which is the total, is W1 plus W2, and that comes to 4.42 into 10 to the power of minus 7 watts. So, LW3, which is the total sound power level, is equal to 10 log 10 and if we do the math, we get 56.455 decibels. Okay. So, this is for two uncorrelated sources, and this is for the case when we have powers involved. We will do another example, and what I will do is I will have the same numbers. So, still we will consider two uncorrelated sources, but I will say that the pressure level LP1 is equal to 51 decibels and LP2 is equal to 55 decibels. So, in this case I am not measuring the sound power level, but I am measuring the sound pressure level, and the pressure level is 51 decibels and 55 decibels. And now I have to calculate the overall sound pressure level, and the question is how do we do that? This is again uncorrelated source. This is uncorrelated source. So, here also the thinking is the same. For uncorrelated sources we have to add up wattage or the energy. That is what we have to now LP1 will give us, will it give us wattage or it will give us something else? It will help us calculate pressure, okay, but it will not help us calculate the energy level or the wattage level. But there is an important thing to understand, and that will help us actually indirectly compute the wattage level also. So, I will explain that. So, consider, and to understand that we will go a little bit on a different track. Okay. Consider a spring, and the spring is having a stiffness K and it is deflecting by a distance delta. Then the energy stored in the spring is how much? K times delta square by 2, okay, K times delta square by 2. Consider a mass and it is moving with a velocity v. What is the energy of this mass? And its mass is m, is mv square over 2. Okay. Consider a capacitor and I apply a voltage of V naught. What is the energy stored in this capacitor? It is C V naught square over 2. Okay. C times V naught square over 2. In all these cases, what you are seeing is that whatever is the excitation, here the excitation was deflection and the energy is proportional to square of that. Here the excitation is velocity and it is proportional to square of velocity energy, and in this case energy is proportional to square of voltage. Okay. Energy is proportional in a spring to deflection square, in a freely moving mass to velocity square, in a capacitor to voltage across the capacitor. Similarly, by analogy, I mean we will not go into detailed rigorous proof, but by analogy we can say that in sound waves the energy which is there is for sound energy is proportional to pressure square, okay, and okay, is proportional to pressure square, and in this case it is pressure P RMS square. So, with this understanding, so what we will do is we will compute P RMS square for both the situations, and then because these sources are uncorrelated, what will we do? We will add up the P RMS squares from both the sources. So, LP1 equals 10 log 10 P RMS square divided by P ref square, and LP2 is equal to 10 log 10 by P RMS square. So, this is second, this is 1 divided by P reference square, P1 RMS square equals. So, if you do the math from this, LP1 is 51 decibels. If you do the math, you find that it is equal to 5.04 times 10 to the power of minus 5 Pascal square, and P2 RMS square is equal to 0.0000126. So, P net square is equal to P1 RMS square plus P. Okay. So, what am I doing? When I am adding up the squares, what am I doing effectively? I am adding up the energies. Of course, it will be multiplied by some constant, because this is proportional, not same. Okay. So, this comes to be 0.000177. So, LP net is equal to 10 log this is RMS and by the way, what was P reference? 2 times 10 to the power of minus 5 Pascals. Okay. So, this is 2 into 10 to the power of minus 5 square. Okay. And if you do the math, you get the same number, 56.455 dB. Okay. So, the point is that whether you add up decibels for uncorrelated sources using the pressure formula or the wattage formula, you will end up with the same number. Okay. So, this is important to understand. So, this concludes our discussion for today. We will continue this discussion on how to add up decibels tomorrow as well. And tomorrow what we will do specifically is to figure out how do decibels add up when the signals are correlated. So, that is all, and thanks for the day. Bye.